Assalamualaikum and good day to everyone who are watching this video. In this video presentation, me and my group members, we are going to present about the chemistry of transition metals. Before we dive deeper, let's take a quick look on the members. My name is Zawadi Numaira, and in this video presentation, I am going to explain about three things: objective, introductions, and also the electron configuration of atoms and ions. Now let us understand what are the objectives of this video presentation. The first objective is to determine the electron configuration of transition metal atoms and ions, highlighting the unique filling of the d orbitals. The second one is to analyze general periodic trends, specifically looking at how atomic size, ionization energy, and electronegativity change across the d block. And the third one is to explain why transition metals exhibit variable oxidation states and how this affects their chemical reactivity. Next is to describe the formation of complex ions and the coordinate bonding involved. The fifth one is to investigate the origin of color in transition metal compounds and why they form such vibrant solutions. And the last one is to evaluate the catalytic properties of these metals and their essential roles in industrial and biological processes. Okay, so what is transition metal? To truly understand this element, we first need to look at the official IUPAC definition. A transition metal is defined as an element whose atom has an incompletely filled d subshell, or an element that can form at least one stable ion with an incomplete d subshell. So in terms of their structure, their electronic structure, we are looking for elements where the d shell contains anywhere between 1 and 9 electrons, and this specific arrangement is what gives them their unique chemical identity. Also, geographically, on the periodic table, the transition metal serves as a functional bridge. They sit between the highly reactive metals and the less reactive elements. And their name actually reflects this transition. As we move across the table, we can see gradual shift in chemical properties as those d orbitals are systemically filled. However, you might notice zinc, cadmium, and mercury sitting in the d block, but technically they are not considered transition metals. Okay, why? Because they don't meet the IUPAC criteria. Their d orbitals are completely filled, containing a full 10 electrons in both their neutral atomic state and their common ionic forms. Because they lack that incomplete orbital, they don't show the typical characteristics of true transition metals. Okay, now I'm going to explain specifically about the filling rules and energy levels. So let us look at how they are actually arranged. So they follow the Aufbau principle, which tells us that the 4s orbital is filled before the 3d orbital. Why does this happen? Because the 4s orbital has lower energy than the 3d orbital. This is because electrons in the 3d subshell experience significant repulsion from the 3s and 3p electrons that are already present. So the 4s orbital, however, is farther away from the nucleus, meaning it experiences less repulsion and is easier for electrons to occupy first. However, there is an important energy shift that we must remember. As soon as electron begins to occupy the 3d orbital, they repel the 4s electrons, pushing the 4s orbital to a higher energy level than the 3d. Writing electron configuration. Let's put this into practice with titanium. When we apply the Aufbau principle strictly for filling, we get the configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d2. But remember that the energy shift we just discussed, because the 3d electron repel the 4s electrons to a higher energy level once occupied, we write the final configuration in order of the principal quantum shells. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, and 4s2. So this reflects that the actual energy state, where 3d is now inside and lower in energy than d4s. Okay, writing electron configuration for special cases. Chromium and copper are two elements that show irregularities and don't follow the standard filling pattern. So this happens because of a stability factor. To achieve maximum stability, these atoms prefer to have either a half-filled or a fully filled d subshell, which provides a more stable spherical symmetry. So let's take chromium as an example. We might expect the chromium to end with 4s2, 3d4. However, to achieve that highly stable half-filled arrangement, one electron from the 4s orbital moves to the 3d orbital. So this gives us the actual configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5.
Firstly, for the general properties of the atomic size, the definition of an atomic size is the effective diameter of an atom determined by an extent of its electron cloud rather than a fixed boundary, and varies depending on the atom's electronic state. First, we will talk about the trend across the period, where to left to the right. Across the transition metal period, atomic size generally decreases at first, then remains relatively constant. This is because as we move across the period, the number of protons in the nucleus increases, which increase the nuclear charge, and a higher nuclear charge causes stronger electrostatic attraction between the nucleus and electrons, pulling the electron closer to the nucleus. As the trend down the group, from the top to the bottom, from period 4 to period 5, atomic size increases. This is because an additional electron shell is added. More shells means electrons are located further from the nucleus, leading to a larger atomic radius. This unusual trend is due to the presence of an lanthanide contraction, where in period 6 transition metals, electrons are added to the 4F subshell. Move on to the second general properties, which is ionization energy. The definition is the quantity of energy that an isolated gaseous atom in the ground electronic state must absorb to discharge an electron, resulting in a cation. Across a transition metal period, ionization energy increases only slightly. As an atomic size decreases across the period, electrons are held closer to the nucleus. However, the increase is not very significant because the added electron go to inner third subshell, and these third electrons provide shielding, reducing the effective nuclear charge felt by the outer electron. As the trend down the group, unlike main group elements, ionization energy generally increases down the group for transition metal. This unusual trend is due to two main factors, which relatively small increase in atomic size and relatively large increase in nuclear charge. Although atomic size increased slightly down the group, the increase is not large enough to reduce the attraction significantly. Move on to the last general properties, which is electronegativity. It is an ability of an atom in a molecule to attract shared molecule toward itself, influenced by its oxidation state and orbital environment. Across a transition metal period, an electronegativity increases slightly, and as atomic size decreases, the nucleus is closer to the bonding electron. This is due to the presence of inner third electron that reduce the effect of increasing nuclear charge, and this limits the increase in electronegativity across the period. As the trend down the group, electronegativity increases from period 4 to period 5, where from period 5 to period 6, electronegativity generally remains almost unchanged, and down the group, atomic mass and nuclear charge increases, and heavy transition metals often have a high effective nuclear charge.
For this slide, I will explain one of the special characteristics of transition metals, which is variable oxidation states. Transition metals are elements that can exist in more than one oxidation state. This means they are able to form ions with different charges in different compounds. This property occurs because transition metals lose both their 4s and 3d electrons during ion formation. The 4s are removed first, followed by the 3d electrons. As a result, the +2 oxidation state is very common among transition metals. If we look at the trend across the transition series, the number of possible oxidation states increases from scandium to manganese. This is due to the increase in unpaired d electrons, which can participate in bonding. After manganese, the oxidation states decrease from manganese to zinc. This happens because the d electrons begin to pair up, making them less available for bonding. Manganese shows the highest number of oxidation states, and this is because its half-filled d orbitals are especially stable. The table on the right illustrates the common oxidation states of transition metals from scandium to zinc, showing how the variety of oxidation states changes across the period. Next, I will explain another special characteristic of transition metals, which is complex ion. A complex ion consists of a central transition metal ion surrounded by ligands. Ligands are molecules or ions that contain lone pairs of electrons. These lone pairs are donated to the metal ion to form coordinate or dative covalent bonds where both electrons in the bond come from the ligand. So, how do transition metals form complex ions? Well, they have a high charge density and vacant orbitals, which allow them to accept lone pairs of electrons from ligands easily. So as a result, transition metals form stable complex ions. The diagram shown is an example of complex ion. The metal ion is labeled as M2+, surrounded by water molecules acting as ligands. Each water molecule donates a lone pair to the metal ion, forming coordinate bonds.
So what is the splitting of the d-d orbital? It is when a metal ion forms a complex with ligands, for example H2O, and the bond between transition metal and the surrounding ligands will create a repulsion between electrons, raising the energy of the d-d orbitals. So this is when the splitting happens. It's because some of the d orbitals have a high energy level, while some have a low energy level, and the colors depend on the matching wavelengths of a certain color in the visible region. So another reason as to why transition metals can produce colored compounds is when the d subshell is partially filled from d1 to d9, electrons can transition from a lower energy state to a higher energy state. But when there is no electrons in the d orbitals, it is not possible for the transitioning energy to happen in the first place. However, when the d subshell is completely filled to d10, there is no room for the electrons to transition from a lower energy state to a higher energy state. Next is the catalytic properties, and transition metals and their compounds are often known as good catalysts, as it can be used to speed up the reactions of the reactions that could take hours for it to finish, and this is due to their ability to change the oxidation states, or in the case of the metals, to absorb other substances onto their surface and activate them in the process. So some of the examples that include these catalytic properties is iron in Haber process, and this combines the hydrogen and nitrogen to make ammonia using the iron catalyst. Next is the nickel in the hydrogenation process, and this is a reaction between ethene and hydrogen. In the presence of a nickel catalyst, will break the bonds between the carbons, filling it in with hydrogens. Vanadium 5 oxide in the contact process is a reaction which converts sulfur dioxide into sulfur trioxide, and sulfur dioxide gas is passed together with air as the source of oxygen over a solid vanadium 5 oxide catalyst.
So let me explain about metallurgy of iron first. Metallurgy of iron is a process that we do when we need to extract iron from its ores by using a blast furnace. Okay, firstly you need to know what is ores of iron. Okay, naturally iron does not come in free form, so we found iron as compound in ores like hematite, magnetite, and iron ferrite. And also these ores contain impurities like sand and clay. So we have the step that we remove all of the impurities to get the pure iron. Okay, so we're moving to the step in the extraction iron, which is we have three. The number one is concentration, 2 is calcination, and the lastly is melting. We're using blast furnace. So for the concentration step, we first see the iron ores is crushed into small pieces. Then we wash with water using gravity separation. The purpose we are doing that is to remove impurities such as sand and clay. And the second step is a calcination. Okay, the concentration ores that we do just now is heated in the absence of air. Okay, the purpose we are doing that is to remove moisture, to remove volatile impurities, and also to make the ores porous for easier reduction. And the last step is melting. We're using blast furnace, which is the concentrated ores is mixed with coke or limestone. And also this mixture is fed into blast furnace from the top, and we using a hot air is blown from the bottom of the blast furnace. Now we move to the reaction in the blast furnace. So we have two reactions. We divide by two reactions. The first one is a formation of carbon monoxide. The other one is a reduction of iron ores. Let me explain the first one first. Okay, as you guys know, carbon monoxide is a reducing agent. Okay, the coke that we mix with iron ores just now are going to burn in air in blast furnace. Okay, and it's going to be formed carbon dioxide, and also it releases a lot of heat, like 1875 Kelvin, so much heat. So the chemical equation is like carbon react with oxygen and getting carbon dioxide and heat. Okay, let's not stop right there. Okay, carbon dioxide are going to further reaction with more coke to get carbon monoxide, CO. Okay, the carbon monoxide are going to reduce iron oxide to iron metal. They are going to reduction of iron ores. Okay, like I'm telling you, carbon monoxide is a reducing agent, so it's going to reduce iron oxide to iron metal, which is ferrum trioxide react with carbon monoxide, and we get the pure iron, ferrum, and carbon dioxide. Okay, the molten iron, we are going to collect it at the bottom of the furnace. Also, function of limestone. Okay, it acts like a decompose of heating, which is calcium carbonate are going to be calcium oxide and carbon dioxide. Okay, the calcium oxide are going to react with silica impurity to get calcium silicate. Okay, and it's float on the top of molten iron. The last part of metallurgy of iron is a commercial form of iron. The commercial form of iron divided by 3, which is cast iron, wrought iron, and the steel. Cast iron just contain 2 to 5% carbon. It's hard but not brittle. Okay. Next is a wrought iron. Wrought iron is the purest form of iron. This contains about 0.25% of carbon. It's very soft and malleable. And the last one is steel. It contains 0.5 to 1.5% of carbon. It's very strong and widely used. It's very common right now. And the product of the blast furnace is a molten iron. It's a slag. Slag is a calcium silicate, okay, and waste gases. Molten iron that we collect at the bottom. Slag is a calcium silicate. They're gonna float above a molten iron, and the last is waste gases leave from the top of the furnace. So as for the conclusion part, transition metal are d-block elements with partially filled d orbitals. They are variable oxidation states, color compounds, complex formation, and catalytic properties arise from d electron. The extraction of iron in the blast furnace illustrates the industrial importance of transition metals.